In this video we discover the matrix and connect its working to the previous videos. The matrix is a very important tool in applied math for various topics and most importantly helps simplifying equation writing. Hi, my name is Alex and this is another video in a series about math for coding with vectors. First, let's review what we found in the previous video. It was about basis vectors and the linear combination we used for a generalized description of a vector relative to a basis or frame. The equations presented there were a little bit inconvenient. Nonetheless, it is absolutely correct and works well. Maybe there is another possibility and more elegant way to represent vector frames. The goal would be to write the operation of basis transformation in a compact manner. So for example, the identity transformation, which simply returns the input vector itself, could be written in a very simple way. In that simple equation, the identity basis could be written as a matrix. But first let us go over some basics about the matrix. A matrix is a collection of numbers arranged in a grid-like structure. The top left entry is the first one and it is denoted as the 1-1 entry. We can reference its columns and rows. Overall, a matrix has m rows and n columns. A single row is indexed by I and a single column is indexed by j. So the ith row and the jth column references a specific entry in the matrix. For example, we mainly work with 2x2 matrices which only have 4 entries, like we see in the picture. M and n do not need to be the same number. For example, a vector is in essence a 2x1 matrix. So in our example so far, the column vector v has 2 entries, v11 and v21. With this discovery in mind, let's think about matrices a little bit differently. That is, we can think of a matrix as a collection of column vectors or a collection of row vectors. Each representation has a specific meaning in linear algebra, which are the column and the row spaces. Either way, we can think of the operations performed on the matrix differently. Let's cover some basic operators. First is the matrix addition. It is very simple. It adds each entry of A and B together. So A11 is added to B11, A21 to B21, and so forth. The subtraction simply subtracts each corresponding entry from each other. If scaling a scalar value is required, we can simply write any multiplier in front of the matrix in order to scale every entry. And finally, the transpose of a matrix. It may not seem very useful at first, but we will see that this operation is very useful in fact. It works by flipping the matrix at its main diagonal, going from the top left to the bottom right. So in our 2x2 matrix example, entry M12 becomes entry 21 and vice versa. In matrix-matrix multiplication, we perform a pairwise scalar product and put the result in the entries of the resulting matrix. So row 1 of matrix A and column 1 of matrix B perform a scalar product and the result is put into the entry 1 of the resulting matrix. Row 2 of A and column 1 of B is combined and put into entry 1 and so forth. The result is a matrix again. Multiplying a matrix with a vector is performed in the exact same way. If we think of the vector as a matrix with just one column, the result will be a vector containing the scalar product of the rows of matrix A with the vector v in each entry of the resulting vector. This was one way to perform a matrix vector multiplication by seeing the matrix as row vectors. The one we know so far involves viewing the matrix as column vectors. End up with the linear combination of the vector entries with the columns of the matrix. Let us revisit the initial goal, which was to simplify the equations and write those more elegantly. First, we had our linear combination which performs the transformation. We wanted the compact form, so we can write a much simpler I times v. The answer gave the previous page with the matrix multiplications. We can now write a linear combination for a transformation in matrix form like so, putting the matrix in front of the vector. Now we do the same with our well-known trigonometric function basis. Recall the linear combination. The matrix is constructed by putting the basis vectors into the transformation matrix column-wise. So Ex goes into the first column of the matrix and Ey goes into the second column of the matrix. Together they form our transformation matrix. Before covering the inverse, let's recall the forward transformation and its notation. The inverse transformation just undoes the transformation. So what matrix M is doing, inverse M is undoing. We start from the left by writing the inverse matrix in front of the vector W. We do the same on the right side. We put the inverse to the left of the matrix M. Resolving the right side, we end up with an identity matrix that leaves the original vector V alone. On the left side, the vector W is transformed by the inverse matrix M. So we end up with the inverse transformation in matrix form. Here is the very important part. The inverse of an orthonormal matrix is always its transpose, which is a much simpler operation and spares us the need to compute the full inverse. This may be trivial in 2D but becomes more efficient in higher dimensions. So the simplified inverse transformation can be performed with a transpose. To summarize the video, we recall the last page of the previous video about basis vectors, because we now know how to interpret the upper letters. Performing a forward transformation puts a vector V from a local space to the vector W in reference space. The inverse transformation performs exactly the opposite transformation. Given the full picture, now we see how simple it actually is to compute the vectors in the spaces using matrices. This was an introduction to the matrix in 2D space. Matrices allow us to simplify the equations for transformations a lot, in a very elegant way. In a later video about affine transformations, we will use matrices a lot, and in fact, the matrix will be the only way to calculate. For now, I am out and stay safe. Bye now.